This molecule is called a sulfate ion. It uses 1 sulfur and 4 oxygen. So I'm going to start off by drawing the Lewis dot models for both the sulfur and the oxygen. Since sulfur and oxygen are both in the 16th group on the periodic table, they're going to have 6 valence electrons. So sulfur will have 6, and oxygen will also have 6. And because there are 4 oxygen, you're going to multiply this by 4. So if you add all these together, you get 30 valence electrons. And then you have to go back and add the extra 2 electrons because it's a -2 ion. So that means there's 2 more electrons. So you have to add those on. And that will give you 32 valence electrons. Now let's draw this. Because sulfur has a lower electronegativity level, we're going to put this in the center, and let's just draw 4 oxygen around there. Then we're going to go in and count how many valence electrons we just used. So we have 2, 4, 6, and 8 valence electrons we used. So let's see how many we have left over. 32 minus 8 equals 24. So because we have 4 oxygen, we need to figure out how many valence electrons to put for each oxygen. So 24 divided by 4 is 6. So we're going to add 6 more valence electrons onto the oxygen. So each oxygen gets 6 more. So now let's talk about the formal charge of the ion. So the equation for formal charge is the number of valence electrons in the free atom, which means the atom that is not bonded, minus the number of valence electrons in the bonded atom. So let's go and count how many valence electrons there are for sulfur. So if we look at the free atom of sulfur, we can see, if you count, there's 2, 4, 5, 6 valence electrons in the free atom of sulfur. So you're just going to do 6, and then you subtract the number of valence electrons in the bonded atom. So let's go count that. It's 1, 2, 3, 4. So you're going to do 6 minus 4, and that will give you a +2. So that means the charge of sulfur in this molecule is +2. Now let's try for oxygen. So if we go back up to the free atom and you count all the electrons again, you will see that there are 6 valence electrons in the free oxygen atom. And then you count how many are in the bonded the bonded atom, and that's 7. So you do 6 minus 7, and then you get a charge of -1. So all of these oxygen atoms, because they have the same number of valence electrons, they're going to all have a charge of -1. So you then add up all of these numbers. So you have a +2, and then you have to add on 4 -1s. And then you should get, that should add up to a -2. So this -2 here is the same as this -2 up here. So that's where the ion is. That's how it's an ion. But these are a lot of numbers here. We have a +2 and 4 -1s. So let's try and see if we can all get these to 0 out, or get as many to 0 out as possible, because we are still going to end up with -2, because it's an ion. But let's see if we can get some of these to 0 out. So let's redraw this. We have our sulfur and our 4 oxygen. And then we need to draw on the valence electrons for all of the rest of the oxygen. Oop, that's too dark. Let's try a lighter color. So these electrons here, if we move those electrons down here, we can create another bond. So let's move those. And then those two will create a bond. So now we've got double bonds here. So now let's try calculating the new formal charge of these atoms in the molecule. So label this formal charge. So let's start with sulfur again. In the bonded atom, there should be 6 valence electrons. So that would go after the minus sign, because it's the bonded atom. So let's go look up at the free one. And if we recount this free atom up here of sulfur, we also get 6. So that would go before the minus sign, because it's the free atom. So we have 6 minus 6, and that ends up equaling 0. So now let's try this for oxygen. So this sulfur atom here now has a formal charge of 0, which is good, because that's what we want. So now let's do this for oxygen. So if we go up to the free atom, we can see that oxygen has 6 valence electrons in the free atom. And because there are 2 different types of oxygen here, we're going to have to do this equation twice. So if we count, we have 6 valence electrons in that atom. So we're going to do 6 minus 6, and that equals 0. So the oxygen atoms that have the double bond are going to have a formal charge of 0. So both of these will be 0. So now let's do this for the other 2 oxygen. So if we go up, so we know that the free atom of oxygen has 6 valence electrons, and this one has 7 valence electrons. So 6 minus 7 equals -1. So these two atoms, the top and bottom atom of oxygen, is going to have a formal charge of -1. So both of these guys. So then you add those -1s together again. So if you add these two -1s, you will end up, so -1 plus -1 equals -2. So we still have a charge of -2. We just zeroed out as many formal charges as we could. So we still have our -2, which is what we want. So that means that this is the best Lewis dot model that we can create. So here it is. So the double bonds don't always have to be in those positions. And what I mean by this is you can have the double bonds on this side, and this whole this whole molecule is equal to a molecule with double bonds going up and down instead of to the sides. So as long as you have 2 double bonds and 2 single bonds in your sulfate ion, it's just going to equal the same. So these are both correct Lewis models. Now for the 3D model. So a straight line just means it's on the face. So it's just a normal line. A dotted line means it's moving away from the camera, and a wedged line like this means it is moving towards the camera. So let's say there's a piece, and double lines mean it's a double bond. So let's say there's a piece of paper in front of this. If you move a piece of paper, these two will line up against the paper perfectly. So let's start off by drawing that. So sulfur is in the center, and then you have the double bonds going out. Then you can see that this one back here moves out, so you do the dotted line. And this one moves forwards towards the camera, so you do a wedged line. This is how you make a 3D model of a molecule. So these are our finished models, our Lewis dot structure and our 3D model of the sulfate ion molecule. The sulfate ion molecule has many uses, and some of them include bath salts, producing plaster, and being electron acceptors.